Alright guys, so last time we talked about our proportions. Prior to that we talked about small and large samples, and so there's one really main concept that we're missing now, and it's the p-value. And it's basically another way of finding whether to reject or fail to reject the null hypothesis instead of using just the critical values and rejection regions and all that stuff. So let's go ahead and get started. So using rejection regions is only one of the two ways to determine the conclusion of a hypothesis test. We can look at the test statistics p-value as well. Now, what does this mean? P-value is kind of like a scary topic in psychology, or in psychology, statistics, anything in that realm. And the reason for that is because a lot of people don't really understand it. So what I want to drive home is what it actually means, on top of how to calculate it as well, right? So we want to make sure we get the answer, but we also want to understand a little bit kind of like what it means, in case there are some conceptual questions that are associated with that. So the p-value is simply the probability of finding a sample as extreme as you did, or more extreme than what you found, right? So what that basically means is that if my null was true, right? If my null says that the average is this, and so the midpoint is, let's say, 70 inches, right? That's the average height for humans. We get a sample that's out here. The probability that's as extreme as that sample or more is going to be our p-value. So let me kind of go over some implications of that and how it all works. So here we have, for example, a z1, just a regular z1. We have a critical value, so it's kind of like our cutoffs. We have a rejection region, and then we have a z2. And so z1 and z2 are kind of like hypothetical two samples, right? So one sample gave me z1, or this is how many standard deviations away from what the null says it should have been. And then z2 is for a second random sample. Okay? So our midpoint is 0, right? That's the null. This is what our null says our average should be, right? So if our average is this, and we got a sample that gave us a z-value of z1, the p-value, if we're looking at greater than, so greater than basically tells me everything to the right is going to be my p-value. So whatever my z is, even if your z is a negative, which that would be mean, but some people sometimes get confused, they're on the left side, so they do a left tail, but you're actually doing a right tail. So even if it was on the left side, it's like you had a negative z3, your p-value is all of this area. So it's 0.5 plus this guy. Does that make sense? I'm going to erase that because it looks a little crazy, but that may be a trick question, and so sometimes professors want to use that just to make sure you're understanding like what a p-value is. If you're doing a right tail test, it's everything to the right, regardless of the sign of that the z-value. Okay? But let's go back to reality and kind of the traditional way of looking at p-value. So here's my critical value. What's this area here? From my critical value all the way down, if we're doing a right tail test. That critical value is our alpha, right? So alpha is the area associated with, here's my z, and that's the probability of it being above that. Does that make sense? So this area here, I'm going to call it p-value 1. And this area here is p-value 2. And don't let the size of my arrows kind of trick you. Let me go ahead and draw them so that they hit the same exact spot. Cool? So there's p-value 1, alpha, and then p-value 2. So what we see happening is that with our p-value, it's kind of associated, it's another way of looking at the critical value and rejection regions and all that stuff. So looking at this first one, here's our critical value. So what would we decide if we got a z2? So if our sample was z2, what would we end up deciding, to reject or fail to reject? If it was z2, we would reject HO, right? Because we're in the rejection region. Does that make sense? But if we'd gotten z1, z1 isn't far enough from the null hypothesis for us to say that, oh yeah, it's definitely wrong, right? So z1 would be fail to reject. Now, let's go ahead and line these bad boys up. So here's p-value 1. Let me go ahead and erase these guys so that it doesn't look too cluttered. So there's our rejection region. We reject if we had Z2. We would fail to reject if we had Z1. Now let's go ahead and put in the probability. So p-value 1 is associated with Z1. Alpha is that second one, and this here is p-value 2, right? So what we see happening is when we line it up, and I put them right below each other so you can see the exact relationship. If my Z is in the rejection region, that means the area to the right of that Z is smaller than my alpha. Does that make sense? So Z2, I'm rejecting it, and what happens when you're in the rejection region? It just straight up, it just always is this way. If it's in the rejection region, that means your p-value, right? So here's your critical value, and where Z1 is over here, as we're moving closer and closer, the probability greater than this Z is getting smaller and smaller. At this point, it's the same as our alpha. Once it gets smaller than that, we're in the rejection region. Does that make sense? So a smaller p-value, you're always going to be in the rejection region. Now the greater one, we fail to reject, and we already know that because it's not in the rejection region, right? But let's look at p-value wise, or the probability wise. The p-value in this case is bigger than the alpha, right? So here's our alpha, and so here's my critical value all the way down, and so this whole area is alpha. Here's my z, right? And this whole area is the p-value. So when the p-value is bigger, that means we're not in the rejection region, right? Our sample is not that extreme. Does that make sense? So p-value is that probability of us finding a sample as extreme as we did, or more extreme than when compared to the null hypothesis as if it were true, right? So if the p-value is small, that means there was a small chance that you would find a sample as extreme as you did. Does that make sense? So even just, not even talking about hypothesis testing, going back to sampling distributions, it's like, what's the probability of finding a sample of 100 people who weigh on average greater than 100 pounds? You know, that's a terrible example. But moral of the story is that that's all it really is. It's just a probability of finding a sample that's this average or greater, right? So if it's really small, that means it wasn't really likely that we would have found a sample that extreme. Now, where's that cutoff? You know, kind of like there's a point where it's like, oh, it's kind of off. It's a small p-value. There's a small chance that that would have happened. Where's that point where it's like, that's too small of a chance. It's not likely to have occurred because of chance, so we're going to be rejecting the null hypothesis. That cutoff is our alpha in this case. Oops. Where is our p-value too small? Where is our sample too extreme? Where is the probability too small for us to say that, yeah, the null is true? Does that make sense? So we reject it. And so then the sample you selected is unlikely to have occurred by chance, and you reject the null hypothesis. Does that make sense? So before what we were dealing with is critical values versus test statistics. Now here, what we're dealing with, and what we're going to deal with for the rest of the practice problems, is p-value, or actually let's say alpha, versus the p-value. And these are both very intimately tied, right? To get the critical value, you need the alpha. To get the p-value, you need a test statistic, because the p-value is associated with the probability of the test statistic being greater or lower, depending on whether you're doing a left, right, or two-tailed test. I feel like I spoke a lot. Let's go ahead and just do a couple problems because I know this is a lot of information, but that's why I have a couple examples that are pretty simple for us to just drive all this home. And so here I have a rule of thumb. So if the p-value is less than or equal to alpha, you're going to be rejecting. If it's greater than alpha, you're going to fail to reject. Now it sounds kind of backwards, just if you understand it, great. If you don't, great. But what I usually tell my students is, you reject the small p. So if your p is small, if the p is small, however you want to interpret that, you're going to reject it. Does that make sense? You fail to reject a large p. Does that make sense? So if these are kind of like crazy concepts for you to really grasp for this moment, for now just know that if your p-value is small, you're going to reject it. Small p you reject, big P you fail to reject. Cool? So there are some innuendos to that. Feel free to make them up as you'd like, but I'm not going to bring that up. But that's just a general rule that's really easy to follow, and a lot of my students really appreciate those little shortcuts. So now let's go ahead and move on to some examples so we can kind of, I guess, bring all this conceptual stuff into an actual problem. So you collected a sample for a right-tail hypothesis test, and I'm doing this very abbreviated. Normally you would extract all this information from a full hypothesis test, but just for the space-wise and just for me to have two like full examples, I put little abbreviated versions. So you read your hypothesis test and you know that you're doing a right tail. How do you know? Because they said greater, you're testing the claim that it's greater than, higher than, more than, whatever. That's associated with a greater than, so you know you're doing a right tail test. And you went ahead and calculated a test statistic of negative 1.25. So what is the p-value for this hypothesis test? So simply, this wouldn't be like a full problem. This is a very abbreviated, very brief version, but just enough for me to go over how this all works. So greater than, that means I'm looking to the right. So it's everything to the right, regardless of whether I have positive or negative z-value. Okay? My test statistic is negative 1.25. And so my p-value is all of this area here. Everything to the right. Does that make sense? So my p-value is going to be all of that stuff. What's the probability from 0 all the way up? So from the mean, or the midpoint of that normal distribution, all the way to its end point, to infinity, the area associated with that, hopefully you guys are saying 0.5. This is kind of throwback from sampling distributions and normal distributions and all that stuff. So how do we find the probability from 0 to negative 1.25? It's just look it up on our table, right? So we look up 1.25 in our table, and what do we get? 1.25, 1.25, line them up, and 39.44. And so you guys are probably noticing that I did this differently. I didn't look inside the table. Why not? Because in this case I have a z-value, so I go from the z-value and I hone in into the probability associated with that. Right? So it's not like we're finding a critical z-value. And some people actually find this probably a little easier or simpler. It's a lot less steps. But conceptually it's harder to understand. So it's a trade-off. So we have, totally forgot the number, and good job, 39.44. So from 0 to 1.25 in terms of z, it's 0.3944. It's the same as if you go from 0 to negative 1.25, right, because of symmetry. So our p-value for this test is what? We just sum up both of those, right? It's just 0.5 plus 0.3944. And so that gives us 0.8944. So that's our p-value. What's usually our alphas? Our alphas are kind of like 0.10, 0.05, 0.02. So pretty much for any alpha, what are we going to decide for this case? Let's say, let me give you a fake alpha. Let's say, for example, alpha was, I'm going to put made up. Alpha is 0.05. Using our rule of thumb, that I have a little box up there, so you guys can see it, I just don't want to scroll up. Using our rule of thumb, what do we decide with this hypothesis test? Do we reject it or fail to reject? We are going to fail to reject, right? So p-value is greater than the alpha, right? So 0.8944 is greater than 0.05. Therefore, we fail to reject. Now, if we do this rejection region-wise, how it would basically work is that my rejection region, if I'm doing a right tail, it's this little area here, right? This guy is going to be 0.05 if that was my alpha, and I find a critical z-value, which if you want to do that, it's 1.645. So anything above 1.645, I'd be rejecting. Does that make sense? is my z statistic greater than 1.645? No, right? So we're not in the rejection region, so we fail to reject again. So either way, I just really want to drive home that these two are pretty much synonymous. They're like brother and sister in terms of how to conduct a hypothesis test. They're all related. Why? Because my alpha is associated with my critical value, and then my p-value is associated with the test statistic. So all it really is am I comparing z's? Am I comparing a critical z and a test statistic, or am I comparing an alpha and a p-value? Basically it. Let's do one more example, because I know we haven't done a two-tail, and two-tail gets funny, so let's have some good times. Well, that was exciting. Alrighty, so again, another abbreviated version, very abbreviated. Collected a sample for a two-tailed hypothesis test, and calculated a test statistic of negative 1.25. So we're back here again, negative 1.25. We did a two-tail, so remember for a right tail, we're concerned with everything to the right, and even for a regular hypothesis test, we're doing a right tail, we have a little right tail, right? If we're doing a left tail, we care about everything to the left, and we have a little left tail if we're doing a rejection region. Now here, we're doing a two-tail. So in terms of rejection regions, what we would have is two endpoints, right? Now in this case, what we have is we're going to be looking at everything to the left and to the right. And so you may be thinking like, oh, to the left of negative 1.25 is some number, to the right of that is some other number, they add up to 1 and you're done. No. Here's where things get a little funky. So whatever z statistic you got, you can do this one of two ways. Essentially, you can put another one over here as a positive. So not what you calculated, right? You calculated a negative one, but you're going to put it on both ends. What essentially you're doing is everything to the left of this one and everything to the right of this one, both of those together is your p-value. But what do we know because of symmetry? Symmetry tells us that regardless of negative 1.25 down or 1.25 up, they should be exactly the same, right? So technically what you can do is, if you want to put them on both sides and add it up, feel free to, or you could just find one and double it, right? Because it's the same on the other end. Either way works totally fine. So let's do this. So we have 1.25. We looked it up in our table already, so I'm not going to really do that. Hopefully it kind of makes sense. So here we have 0.3944. And what's left over? How do we find this little area here? The p-value then, which is that area, right? The p-value is going to be 2 times, right? And I'm doing 2 because it's a two-tail test, so I'm going to double the p-value. So it's kind of like the reverse of what we did with the alpha. Normally with the alpha we split it in half. P-value, we're going to double it so that we get the full p-value. So 2 times, and how do we get this little area? It's 0.5 minus 0.3944, right? So 0.5 minus 0.3944, that gives us 56, or 1056. So 2 times 0.1056. And from there we just double that, and so we get 0.2112. So that's our p-value. And let's say again we're using an alpha of 0.05. Right, so I made up an alpha of 0.05. My p-value is still greater than, right? Still greater than that alpha. It's still greater than alpha, so we decide to fail to reject. And why is that? Because even if we had negative 1.25 and 1.25, a p-value, an alpha of 0.05, two-tail giving me 0.025 on both ends, the rejection region is going to be somewhere over here. So here's going to be like our critical values. And so even if we did it with rejection regions, we would find that our test statistic lies within that outside of that rejection region, right? So it's not on those outer ends. It's somewhere kind of in the middle. There's not enough evidence for us to reject the null hypothesis. Therefore, we decide to fail to reject. Now, tying it back every single time to the critical values because we just finished seeing that, so it's a whole new different topic, but I want to bridge that back to what we saw before. So that's about it for our conceptual piece. Now we're going to do a couple more practice problems in order for us to make sure that we get this all down packed. So let's go ahead and move on to practice.